Recording. Okay, start recording. Yeah. Well, so we have done in the last lecture this Jacobi, right? Jacobi method. And this was the formulation which is written in matrix vector form, and this is the formulation written in the component form. Now pay attention to this component form. May I write this component form in this form also, because this summation, if you take a look here, what is that summation? J goes from 1 to n, but except that I term, right? The middle term when you reach. So it is not exactly AX, but you are not using in the multiplication that diagonal entry. There you have kept actually 0, 0, 0. So this I can split further, that I will do the two summations. One is when j is less than I will do this one, and then j greater than I will do this one. So I'm actually doing this one exactly, the complete sum here, which is j goes from 1 to n, j
So
not
we are
equal
separate. So we are
to,
separating the lower and upper sums.
yeah, so here we have taken up to I, and then here j goes from bigger than I. So j equal to I is automatically not there here in this summation, right? It is same summation as this one. Here we have
Yes, sir.
considered two. Clear? Is that clear? This is step
So
that
the
here that
first summation is
summation.
the lower one, right?
Sorry.
So the first summation aij where xj where j less than I, it is the
Yeah,
lower one, right? And the
it is the
second one is the
lower
upper
one.
one.
This is the upper one. Yeah,
Yes.
true. Fine. So this summation was just splitted into two again, but same thing. There is no difference in this and this one. These are the same thing. While doing examples, we will do this. This formulation looks a little more complicated than actually it is. When you will be doing computation, there will be no such problem. Now you just pay your attention here in Jacobi method, because I'm going to introduce you the other one, the Gauss-Seidel method. Here what is happening, that this in the first sum is going xj is moving up to less than I. So we are computing here ith component. The first sum is using xj's before I, and the second sum is using xj's after I, right? I plus 1, I plus 2, and so on. These x are being used, and here 1, 2, they are used up to xj minus xi minus 1. This j goes from 1 to I minus 1, and this here it goes from I plus 1 to the n, whatever component we have, right? So this Gauss-Seidel method was developed, actually it's just to like improve this Jacobi method. The idea was that when you are computing this ith component of that vector, you have already 1, 2, 3 I minus 1 component, because you start with x1. Yeah, you have computed x1, the first component of that vector. Then you have computed x2, the second component of that vector. I'm not talking about the iteration. I'm still at some fixed iteration, k plus 1 th iteration, but I am updating my components. So x1 is updated, x2 is uploaded, x3 so for example, when I am updating x3, x1 and x2 are already updated, right? But this formulation is not using those. This is using from the previous iteration. Is that clear? This
So can you please
formulation,
explain again?
Yes, sir.
this form. So when for instance, I am computing x1 now at k plus 1th iteration. So this formula will use everything from k plus, kth iteration, right? All x, j, whatever is being used, they are used from kth iteration. When I compute x2 also, anyway, when I am computing x1, I don't have anything new. So it is the first component I'm computing. So naturally, I will be using previous iteration values. But when I compute x2 at k plus 1th iteration, the second component, now there are two ways. One is that I still use everything from the previous iteration, from the kth iteration, which we are using here in Jacobi method. But you should have this question in mind that why, if x1 is available now, which is supposed to be, newly computed value, better value. So why don't we use that x1 wherever x1 is coming? Can we use this newly computed value of x1 instead of using x1 from the previous iteration? So which one looks better? Yeah, you tell. That we should use that newly evaluated value, which is supposed to be better, because in each iteration we are actually expecting something improved from the previous iteration. So naturally, if x1 is available with me, why not that we can use this x1 and then x2 is evaluated, then while computing x3 we should use all these x1 and x2, and then x3 can be evaluated. So that is another way which actually Gauss-Seidel method does, that it uses all very newly computed component. It does not wait to go for the next iteration to use everything from the previous iteration, which Jacobi method is doing. Jacobi method is doing that first iteration, all values are computed, fine. When you go to the second iteration, it will use in this computation all the values from the previous iteration. Whereas the idea of the Gauss-Seidel is that whatever is we have evaluated in this iteration also, we will use those values. Are you following me? Just say
like in the one step of matrix calculation, like the calculation of that elements.
Yeah. What was your question?
I was muted actually. Like in the calculation of the like elements, further elements, we are using the previous elements that we have already calculated. That is the idea, right?
That is the Jacobi method.
No, sir. I'm saying like suppose we are calculating the third element in one step in Gauss-Seidel method, and we are using the second and the first elements to do that.
Yes, true. So we have computed first component, we have computed, for example, when we are computing the second component, we can use that first component which was just computed in this iteration. And then for computation of x3, we can use x1 and x2. But Jacobi was not doing that. Jacobi was doing everything from previous iteration. Clear?
Excuse me, sir.
Yeah.
Yes, sir.
So, but in this Gauss-Seidel method, we are using the another means I component. But how can we use that? Because we have to take components from previous iteration to the next iteration. The same component we have to take. So how can we take the first component to the second component?
Yeah, see here, that's what, just look at this new formulation, which is the Gauss-Seidel one. This is Jacobi. Just compare from the Jacobi one. You have xi k plus 1 over aii, same. This is also same. This was the sum where we could have used those recently computed values, because this xj, j is going up less than I. J is like 1, 2, 3 up to I minus 1. But those have already been computed because we are computing now ith component. So here that's what we have replaced here, k plus 1, because these values are already with us. K plus 1th, these values are with us, and these we don't have, so naturally we will use from the previous iteration. Is that clear?
Sir, in the last one, we can also use k plus 1 for j greater than I. So for j greater than I, we can also use k plus 1.
No, value. But we don't have those values. Here we don't have those values because you are computing ith at present, and these are even bigger than ith. So you are talking about I plus 1, I plus 2, I plus 3. Those values we don't have at k plus 1 iteration. We are just evaluating.
Okay.
True?
So I had one question.
Yeah.
Sir, like I understand that the approximation will be probably better, but doesn't it break the equality? Like the equality only holds for Like the previous values if they are used.
See, those equalities never holds. They are, if you go with the actual solution, if you go with this equality holds, if I have the actual solution, this equality holds actually. This is the equality. This is the equality.
These are just approximations, so they will
So
never
these
hold
are
in
approximations.
truth.
So
We are just assigning.
these are kind of numerical approximations. So these are not actually equality in terms of the actual solution, because actual solution fulfills this one. This is for actual solution. X is equal to d inverse L plus 1 x plus d. So here is actually in equality in terms of the actual solution. But these xk plus 1 xk, these are approximations. Yeah. So you don't need to, worry about those equality disturbance and all.
Sir?
Yeah.
Sir, actually we are approximating our value first guessing some x.
Yes.
So sir, we are actually approaching to the answer or diverting from our answer. How to know, sir?
Yeah, so those things we will just learn. So at this moment we are up to the formulation only, that some kind of splitting, and then we have set up these iterations, and now we are expecting that we will get the answer, right? This is the only thing we have done so far. So we have not reached to that point whether this scheme, this one is better, or this one, even we don't know whether this one is really better. That also we don't know. That whether this Gauss seidel is better, at this moment we don't know. Clear? But we have done some kind of approximation. So those questions will be answered. Yeah.
Sir, here in Gauss seidel method, we are assuming that we are calculating x1 first, then x2, then x3
Yes.
till xn.
Correct.
Okay.
Yeah.
We can
First
calculate,
x1,
but
then x2,
first,
x3.
sir, suppose we calculated xn and then we again resubstitute in, so in the j greater than I part also we have all the components. So we
You
can
mean
again
you have to
resubstitute.
go backward kind of thing.
Yes,
That
yes. First we go
xn,
forward and then
then
again we go
xn
backward.
minus 1, then xn minus 2, then probably you will be using obviously in the second one.
No. First from x1 to xn, then and then again xn to x1.
No, either you go x1, x2, x3, xn, or you go xn minus 1, xn minus 1. I mean, y2. You will go, let's say x1, x2, x3, xn. We will compute like this.
Yes, sir. So we have all the components now, but actually the in xi power means k plus 1th iteration, the last term j greater than I term is still approximate. So
Yeah,
we
it is
can.
from previous iteration. It is
So
from
we,
previous
but
iteration.
now after calculating x1, x2, x3 till xn, we
Huh.
have all the components. So again we can resubstitute and get xi
But that
k
is
plus
what
1th.
we are going to the next iteration.
That will be k plus 2, I guess.
Then k plus 2. So you are done with all computation in one particular iteration, and then you want to substitute again, means we are going to the next iteration, isn't it?
Okay, sir.
So we'll go to the next iteration, of course. We'll be using those. So this is not just one time process. Yeah, you have to keep on doing this.
Excuse me, sir.
Yeah.
Sir, xj will be just previous element, or we can take any element previous than I.
One. So this is, if you are using k plus 1, you get from kth, just previous one, from previous iteration. Why to use?
So sir, xj is xi minus 1 basically. Xj will be xi minus 1, right?
Xj will be, which xj you are talking
Xi
about?
minus 1. Sir, in those formula, xj means just previous before I. Xi minus 1.
In the second summation, xj here. So this j is more than I plus 1, I plus 2, and so on. And here this j, so this lower indices are for the component of the vector, correct? And the upper one,
sir,
the
suppose,
k,
hello.
this is the iteration one. The upper
The one
is
in the bracket is the iteration number.
You are talking about
Those are the
iteration,
components
right?
of the vectors, the I and
Yes,
j.
sir, iteration number.
Yeah, so iteration number is here, k plus 1th iteration, these values. Here k plus 1th, here kth iteration. These are iterations. Yeah. Let's do some example. I think many of your questions will be cleared. Otherwise, we can get back to at that time itself. Yeah. As I said, this is very kind of trivial things once we do that there in the examples. Okay. Shall we proceed?
Yes, sir.
So this is Gauss Seidel method. The only difference is that here k plus 1 is replaced because these values are already computed. If we are computing x1, x2,
one question.
yeah.
So one trivial question, like we have to perform this iterative method over a number of times. So we have to do it manually, or like it will take a lot of time then to reach the
Not
convergence.
usually see all these iterative methods are for computers. Yeah. Not
Yes, sir.
of doing by hand. By hand, you can do one iteration, two iterations, and so on. But that will not give you the solution. Yeah, the solution may come after 100 iteration or 500 iterations or whatever. Yeah, depending on how slow or fast is your this is speed which is taking you towards the actual solution. So they are done obviously in the computer. You have to code in some programming language and then you can use these methods. And as I mentioned before, also these iterative methods are for large system when you are dealing with the really 1000 by 1000 matrix or 10,000 by 10,000 matrix and so on.
So in this course, so what will like what kind of
In this course, so you because the aim is that you understand these, right? So we'll give you 3 by 3 and then you can go for we can ask you just after one iteration what will be the value or after two iterations what will be the value. That's all. Okay. Simple calculations.
Okay, sir.
Yeah, so just to put again back to matrix vector form. So this is easier path now to go from here to here. So you remember this is like in vector form xk plus 1. This is d inverse and then you have b there. And this is L. There also it was lxk and uxk. So now here lxk plus 1 and upper one will go up to xk plus 1. So again the same thing but written in matrix vector form. And finally, because this is also lxk plus 1, this is also lxk plus 1, you first multiply by d to the whole equation, then you have d plus 1 xk plus 1 and then finally you have this equation xk plus 1 is equal to minus d plus l inverse uxk plus d plus l inverse and this b. Fine. So this is the matrix vector form of the Gauss-Seidel method. True. So let's go to this because I'm sure here this will be much better now to make you understand. So here we want to compute x1 after one Gauss-Seidel and one Jacobi iteration method. Only after first iteration what will be the new values, this we want to see. These are the three equations. Fine. The best trick is if you want to do component wise, you don't have to remember any formula which I have given you before. If you just want to compute for this small system, catch the first equation. You write down x to the left hand side. Rest everything you bring to the right. Y minus 2z and divide by 5 also, right? From the second equation, you write down for y 12 minus x minus z divided by 3. From here you write down z 8 plus x minus 2y is equal to divided by 4. True. Put the iterations. I'm using Jacobi method for instance. So here k. Oh, sorry, this is k. Right hand side kth iteration. K plus 1 k. This is your Jacobi method. That's all. Give the initial guess is given already 1 1 1. Put 1 there, and get the x. Put 1 here, x z. Yeah, this is z. So 1 1 and compute this. This is your new y. Put xy, you get new z. This is your Gauss-Jacobi method. If I want to get Gauss-Seidel, obviously x will be computed as it is. There is no change. You will put initial guess there, the right hand side here, initial guess, you will get new x. So the x in both will be same. But now when you compute y, in the Gauss-Seidel, in the Jacobi, you was using x as 1 from the previous iteration. But now since x is already computed, so you will using here x plus 1. So the recently evaluated one, x plus 1. And z obviously from the previous one. Then you compute z. When you are computing z, x and y are known. So instead of kth iteration, you use the new one, k plus 1th iteration. Fine. So this is x, y, z.
Yes, sir.
Yes, sir. Understood.
So let's do it. So here, this is a system of linear equation. Yeah. Any question?
Sir, can we take y from first equation rather than x?
Well, that meaning is that you are actually shuffling your equation. That you want to take, for example, y from there and x from there. So first component x you want to take from this equation. So the meaning is that you are actually considering this equation first and computing your x and so on. Because if I want to write in a matrix vector form, I need that coefficient matrix A. So what you are asking me that can you change the order of equations? Yes, you can change, and your answer will be also different. Your answer will be also different, and this may happen. I will cover those cases also, that order matters. In a particular order, the method may converge. Wherever you change the order, the method may not converge. That may also happen. Yeah, so we'll come to that point.
Yes, sir, I got it. And one more thing, sir, like, is there any rule like in first equation 5x plus y plus 2z is equal to 13, and 5 is the largest coefficient, right?
Yeah.
So you took x from that, and in second equation it is 3 and you took y, and third equation it is 4 and z.
Yeah.
Is there any rule of that sort or nothing?
So that also will come in a minute when we talk about convergence. So if this coefficient matrix like 5 1 2 was in this present form, right, without changing the order, 2 4, this is our coefficient matrix A. So if the coefficient matrix is diagonally dominant by rows, right, which is the case here, that 5 is bigger than the sum of the rest 2, 3 is bigger than the sum of the rest 2, 4 is bigger than the sum of the rest 2. So if that is the result, which is a theorem, that if your matrix, coefficient matrix, is in diagonally dominant form, then definitely your Jacobi and Gauss-Seidel method or other iterative methods will converge. So that is important. If I change the order, for instance, this will not be a diagonally dominant matrix anymore, and in that case the method may converge, may not converge. Then we have something else to check. So, but if it is diagonally dominant, we are sure that it will converge. If it is not diagonally dominant, that we will learn, then we have to check something different, something else. Is it okay at this moment?
Yes, sir. Like, but how can we, on what basis can we say something like diagonally dominance will surely converge?
That's what I said. It's a standard result, which I can give you some kind of proof also there. Yeah, some very little, short proof. We cannot go to very much into the detail, but a quick, I can give you some intuition that how this is working.
Yes, sir.
Okay. So while computing this, yeah. Yes, quick. Now your voice is not clear.
Dominant.
Hello. Am I?
Yes. Yes, tell.
Sir, what does mean diagonal dominant?
I explained you before. You were present in the last lecture and today also. In the beginning, you missed that portion. So diagonally dominant means that the absolute value of this diagonal entry, which is 5 here, is bigger than the sum of the rest. So absolute value, of course, which is there here in this row. In this row, the second row is also clear. 3 is greater than 1. Absolute value plus 1, that is also done. In this row also, 4 is the diagonal entry. Absolute value is same. So absolute value of -1, that is 1. And plus 2 absolute value. So this is also holds. So the diagonal
So
entry
here
is
it is strictly diagonally dominant.
every
But here
diagonal entry should be bigger than that row entries, the other sum of the other entries in that row. And then the matrix is called diagonally dominant matrix.
So I had a query. So in this particular matrix, it is strictly diagonally dominant.
Yeah, strictly diagonally dominant. In this case, it is strictly diagonally dominant. Correct? Fine. So while writing for the Jacobi method, as I said, from the first equation, you write down x and y0, z0 you use. There was 1, 1, 1. All the three values. We started with 1, 1, 1. We can start with 0, 0, 0 also, and we will discuss that. Does it matter that what initial guess you take? It matters only for the convergence, that it may be faster if you have taken a nice guess, which is nice in the sense it is close to the exact values or more realistic. So then you may get just the actual value. You can be close to the actual values faster than choosing some guess which is absolutely different from the solution, but it's a matter of few more convergence, that's all. But it will converge. The convergence will not depend on the initial guess. So it's just 2 here, right? So x1, the updated value of x is 2. Now I'm using y from the second equation. And again, here I will using 1, 1, 1. I have 10 by 3. Now z, I have this 7 by 4. Is that clear, this computation?
Yes, sir.
These are my new values now of x, y, z using Jacobi method. Now if I want to compute x2, y2, means after second iteration the values, you have to use these values here now, not 1, 1, 1. 1, 1, 1 is over. You have used already here these 1, 1, 1. Now in the next iterations you have to use 2, 10 by 3, 7 by 4 and get the new values. Fine? Is that clear, the idea? And then third iteration, fourth iteration, fifth iteration, 10th iteration, and so on. Now Gauss-Seidel method. This first component, evaluation of first component will be the same. There is no change. And the value is 2. Now for the second one, see, instead of x0, I can use this x1. That is the only change. That means I'm using here 2 instead of 1. And then the value is 3, which is different from the Jacobi one. Now computing z, I'm using x1, which is already evaluated here as 2, and y1, which is 3 now. So I'm not using anything from the previous iteration in this equation. So when you compute this, you are getting 1. So this is the Gauss-Seidel one. And then in the next iteration, you use again these and so on and compute. Is that clear?
Yes, sir.
So I hope no question in this evaluation part. So starting with this initial guess, perform one iteration using matrix form. So let's do it matrix form because sometimes this is also useful. when there are many programming languages like MATLAB you have heard, so which uses mostly the matrix vector multiplication. So instead of doing this component wise, which we have done just before, you can program there and then you can use all matrix vector multiplication, and that will be quick, just one line, two line in this algorithm. So for the Jacobi method, you have to remember that this was the iteration matrix. So we have to compute. So D, so see, A is your 5, 1, 2, 1, 3, 1, minus 1, 2, 4, right? So now here you have D inverse, oh sorry, D inverse you need to compute. So first D is 5, 3, 4, and that will be 1 by 5, 1 by 3, 1 by 4 will be the inverse. L plus U, so except this, diagonal entries, the rest coefficient matrix is L plus U, A minus D. Okay, so this is your, for Jacobi method, the matrix, the iteration matrix, and the iterative scheme was this, if you remember. And starting guess you put here, then this B there, D inverse here, then this Jacobi iteration matrix, and then you compute, and you will get this 2, 10 by 3, and 7 by 4. So this is the way you can do calculations, and then use this one here again, and you will get the new value. The new value use again and get the new value, and so on. So this is simple. The Gauss-Seidel method was this structure here, L plus D inverse and U, and then again L plus D inverse there. So you have to get L plus D, then you have to get L plus D inverse, and yeah, so just put it there in this form here, L plus D into U, then D plus L inverse, and again there's a lot of matrix multiplication. And so this is our formulation now, the Gauss-Seidel formulation. You put the initial guess here, put initial guess there, 1, 1, 1, and so on. You will get 2, 3, 1. And then this 2, 3, 1 again, you can put it here, you will get the next value. That value, put it here, you will get the next value. So you can compute using matrix vector multiplication, also the same thing. Is that okay? Is that clear now? That you can use matrix vector multiplication, you can use the component wise. If it is not asked for matrix vector, then you can directly use that component one. For a small system, there is no problem. If you are doing by hand, just go with what we have done before.
Sir?
Yeah.
Sir, how we will check that this solution is right? By same method, by calculating the error?
Yes. So the question is actually where to stop, right? These iterations. Yes. This is not the solution. This is not the solution, right? This is just the first approximation.
Yes, sir.
Then you put here a third approximation, fourth approximation, and so on. The best is that because you know Ax is equal to B, that system of equation you know. So as I said, you get the residual B minus Ax. Compute this, whatever is your recent value of X, put it there, B minus Ax. So you compute this residual vector, and then the norm of this vector will give you that idea how large is this vector. Any norm which we have discussed you can consider, and they will give you the idea, because that value should be close. That norm of this should be close to 0 of this, because this R we are expecting something like close to 0, 0, 0, all components close to 0, 0, 0, right? And then that means your approximation is pretty good. So that will be depending on this residual, which you can compute always. B is known, A is known, X you are computing these values. So this, how large is this vector A, or how small is the, sorry, R, how small is this vector R, that will depend on. So if it is very small, you can stop it depending on what accuracy you want to set. If you want to go very, very accurate, that means you need this R, very, very, very small matrix, very much close to 0. Vector, very close to 0 vector. Fine. So that you, because the actual error you cannot compute, because we don't know the actual solution, right? We are computing for those problems where we don't know the actual solution. So you cannot compute the difference between the two vector and decide. Clear? So next question here, solve the system using Jacobi-Gauss-Seidel method, perform 3 iterations using initial guess. Anyway, it's the same thing. So I don't think we have to spend now more time here on this. So this is the Jacobi method, right hand side, for every component we are using the k there. That means we'll be using this initial guess here and we'll compute the first iteration. So this is the first iteration values here we have computed. Then these values will be used for the second iteration and for the third iterations. So that's a matter of computation, but I don't think there should be any confusion in this. Okay, so the Gauss-Seidel is again here x1, x2, x3, and initial guess is given. The only difference here is that this is k plus 1 and here both the places k plus 1. That is the only difference. You have to consider, you have to take care, like you can see here this 0.475 I have used, which was just calculated, just evaluated. And in the third component I have used this 475 and I have also used this one recently evaluated. That is the Gauss-Seidel method. So you can compute similarly the second iteration and the values after third iteration. You can use your calculator, in fact. That's fine. Now we will come to the convergence issues, which you have many questions, of course. So is that fine now? The evaluation part, that a problem is given to you and you can compute the different iteration values.
Yes.
Yeah, either to use matrix vector or use this component wise, whatever way, but I think you can do that, right?
Yes, sir.
Okay, so next 5 minutes we'll go with the convergence one, but definitely we'll continue tomorrow and finish this everything there. So the iterative methods, the first is called the necessary and sufficient condition for the convergence. Necessary and sufficient. So it's a very good condition, because necessary and sufficient means that you can understand whether it will converge or you can understand whether it will not converge. You can conclude both the things, convergence, non-convergence, when we are talking about necessary and sufficient condition. Later on we will also come with some sufficient conditions, but this is the most important one. If you can check this, everything is clear, whether it will converge or it will not converge. And the condition is the iterative method converge for any initial guess if and only if all the eigenvalues of the iteration matrix G have absolute value less than 1. You see now the eigenvalues. So those eigenvalues will tell you for a given problem, write down the matrix G, the iteration matrix G, compute its eigenvalues, and if all the eigenvalues are less than 1, the absolute, in absolute sense, if they are less than 1, if their absolute value is less than 1, then the method will converge for any initial guess. And if any of those eigenvalues are greater than 1, then it will not converge. So I think all your questions got clear here now, at least with this result. How this result is coming and so on, that is another question. Probably I'll give you some idea, but not the complete details of this result. But more important at this stage is whether you understand this or not. Did you get the point? How to check the convergence, whether the given method will converge for that given problem or not?
Yes, sir.
For that, to
Yes,
get
sir.
eigenvalues. That is another
so
question,
since
that
the
eigenvalues may not be easy. Yeah, please ask.
like I was saying that since the G matrix in Gauss-Seidel and Jacobi method are different, it may happen that for the initial same guess, like
Yes.
Jacobi method converges and Gauss-Seidel does not, and the reverse.
One may converge, other one may not converge.
Yes, sir. Yes, sir.
Yeah. Same problem, same initial guess anyway is not playing any role. So this is for any initial guess will not play any role. But yes, it may happen that one is convergent, other one is not convergent. Fine. So or this result is also written in this form.
Can you please repeat the previous point? I didn't get it.
Repeat the
previous doubt that you answered. Can you please repeat that?
The answer, the question was whether for a given problem, can it happen that Gauss-Seidel method converge and the Jacobi diverge, or Jacobi converge and Gauss-Seidel diverge? So the answer is yes. It may happen that for a given problem, Jacobi method may converge, Gauss-Seidel may diverge, or the other way around. That will depend on the iteration matrix, because iteration matrix are different for both the methods. So one iteration matrix may have absolute value less than 1, other one may not. So that we cannot guarantee that this Gauss-Seidel will converge always, or I mean, for a problem, if Jacobi converge, Gauss-Seidel will definitely converge. We cannot say anything. I'll show you many examples of those natures to clear your doubt. Yeah.
Got it, sir.
Got it. Okay, so this result itself we can write in this form also. The iteration method converge if and only if the spectral radius is another term which I think is new to you. The spectral radius is used as the largest absolute eigenvalue. So if you have like 1, -5, 2 are the eigenvalues of a matrix, then spectral radius is, what is spectral radius? It is 5. Yeah,
5.
The largest absolute eigenvalue, that is the spectral radius. So that spectral radius should be less than 1. That is the idea, which is same as the same meaning what the above result is saying, that all the eigenvalues should be should have absolute value less than 1. So if all the eigenvalues have absolute value less than 1, definitely the spectral radius is less than 1. So instead of saying all the eigenvalues less than 1, just say if a spectral radius is less than 1, the method will converge. If the spectral radius is not less than 1, it will not converge.
So how did we get this name?
Is it called a radius?
How?
Sir, why spectral, why radius?
Why? What is spectral? Again, you repeat. You repeat your question.
Sir, why is this called so? Like, why is this called spectral radius?
Oh, why it is called? Okay, it's a well-established term, so I don't know how this name has come there. But spectral radius, so I don't know. I mean, why this name spectral radius was used in the literature. But this is a unique name, I mean, which is used for the absolute, for the largest absolute eigenvalue. It's called spectral radius. Yeah. Yeah, there must be some reason, of course, for radius we have to look for.
Sir,
Yeah.
for example, like in complex number or in complex plane, when we write that mod z is less than 1, it tells about the area inside a circle of radius 1 unit. So it's something like that. I mean, the inequality, something like that.
It can be because see the eigenvalue can be real or complex. Yeah, so if it is a complex, it's giving you similar kind of notion that that radius should be within that disk. All the eigenvalues should fall within that
given
disk
radius
1. So, but why spectral and all, I don't know, huh?
Excuse me, sir.
Yeah.
So if a spectral radius is greater than equal to 1, then it will not converge surely, or
yeah,
it may
that is the necessary and sufficient condition. Exactly. So that's a good point here. So if the spectral radius is greater than 1, then you also know that it will not converge. So everything is known. Once the eigenvalues are known, then actually you know about convergence and non-convergence both. You know about convergence and non-convergence both. So that's the beauty of this necessary and sufficient condition. There will be some sufficient condition. That one of them I mentioned, if you remember, that if the matrix is strictly diagonally dominant, if the coefficient matrix is strictly diagonally dominant, then the method will converge. But we don't know about if the coefficient matrix is not strictly diagonally dominant, what will happen? That we don't know. The method may converge, method may not converge. So that is only one-sided. But this is necessary and sufficient. So both the information is available here. Yeah. Good. So I think we are done with this. So we'll start tomorrow because now time is not there. Much time is not there. Yeah. So you can go for your other class.
Thank you, sir.
Thank you, sir.
Great. Have a good
Thank
day.
you, sir.
We'll discuss tomorrow.
Thank you, sir.
Thank you. Thank you. Hello.
Thank you, sir.
Thank you, sir.